Welcome back. So sometimes it's not the analyst that's the problem. It can be the tool. So let's talk about borked tools. The most broken tool known to data science is Microsoft Excel. It causes more crying in my hands than any other tool. So the mistake made here is using Microsoft Excel. No, I'm kidding. Really, the mistake that we're going to talk about is unintended interactions of data and common pipelines for analyzing data. So Excel being a very common way that data is analyzed, even in data science, we have to understand the interactions we can have with this tool. So this particular example comes from my world, where I do a lot of genomic analysis. Okay, so you take biological samples and run them through these magic machines, and these magic machines come up with a list of genes that are in the sample and how much of the gene is being turned on and making proteins which make the cell go, right? So you turn on genes and get them to throw some proteins out for the cell to do its thing. So how many genes are on and active versus how many genes are shut down, and what are those genes? So this kind of data is huge, right? We're talking about, there are, just in terms of protein coding genes, there's, almost 30,000 of them. And then there's a lot more bits of non-coding DNA that do other things. So it's a big deal. There's a lot of variables. Okay? So many of these variables have silly names. It's been a long tradition in biology that whoever discovers a gene gets to name it, and sometimes these names are things like literally Sonic Hedgehog, for those of you that are aficionados of old Sega games. Sonic Hedgehog is the name of a gene. So are things like FOXP2 and, IL6 and really bad names like that. So there's a set of genes called septins. They make, there's a whole family of them, and there's like septin 1 and septin 2 and septin. So whenever you write sept to Microsoft Excel, it can only think one thing. It thinks calendar. It thinks September. And it turns genes into dates for you. Isn't that nice of it? So I have multiple times been handed data that went through Microsoft Excel. Some biologist did some experiment and copy pasted the output of a machine into Microsoft Excel and manipulated it and saved it. And it turns out that all the septin genes now say September. And other genes get turned into just random floating point numbers. Okay? And it gets even worse because when you use columnar data like pandas and R in data frames, if the first item in the column is a date, then everything below that column will become a date. Lovely. All the data turns into dates. So none of it is a calendar. Please, Microsoft, stop. Well, they didn't stop. They have no reason to stop because that's convenient for their users in other circumstances. So it's just our poor genomic scientists that have to suffer with this problem. And in the end, what's happened is that there's been a proposal to rename genes like septin to something else. So we're just going to change biological science, the whole endeavor, instead of waiting for Microsoft to get around to fixing this problem, which is multiple decades old. So this kind of Microsoft Excel stuff is so prevalent that there's an entire website dedicated to Microsoft Excel horror stories. So always worth a little laugh. I'll let you explore that on your own. Now, another mistake people make with genomic data is just using procedures wrong with it. It's big and complicated. As I mentioned, there are 30,000-ish genes that you might be interested in. Some of the other techniques that use little probes, they use microarray probes. They can have hundreds of thousands of little bits of protein that they're recognizing. So when you have that many variables, it's a very big problem. Most of the time, you can't do an analysis with tens of thousands or hundreds of thousands of variables. What you're going to do is you're going to try to figure out, hey, which ones of these tens of thousands or hundreds of thousands, which ones of these are actually relevant to my problem? You're going to do something called feature selection, which is usually done with cross-validation. Now, we've just barely covered that in class, but to remind you briefly, if you're looking for how you're going to train a machine learning algorithm, what you're going to do is you're going to try to understand its performance levels by breaking up your data into a training set and a testing set, or a training set and a validation set. You're going to train on the training set, and you're not going to let your algorithm learn anything at all on that test or validation set. You're just going to run it forward through it, get the answers, find out how close are they to reality. Are the answers very close to what they should be? Well, good job, you. Are they very far away? Well, maybe this is the wrong model. Maybe we should try something else. Okay, so when you're doing cross-validation, which is a way to do this train test repeatedly, then you need to make sure that you have done the feature selection, looking for the numbers of variables inside that cross-validation. You don't want to use all of your data to figure out which genes you're going to regress on, you're going to put your regression on. If you put your regression on genes that you select when you look at all your data, then you've leaked information from your test set into your training set. You now know things about your test set. You know that these genes are a good idea if you're trying to understand things in the test set. So that kind of data leakage is a big problem. And it happens a lot, it turns out, in genomics. So that's what this whole little Twitter thread is about. This person, Jacob Schreiber, has found that there is loads of this stuff going on in the literature where people are reporting, okay, I fit my line on top of this genomics data, but first I figured out which genes I was going to look at based upon all the data. So they didn't cross-validate to find the relevant genes. And it's even worse. This is also a tool problem, right? So it's a tool problem because the dude looked inside a very commonly used software pipeline in genomics and found out that this tool does it. It does it for you. And so many biologists are going to use this tool, and they're going to use it dumbly because they're biologists, they're not trained in data science. They're just going to use this tool. They're not going to know what's inside it. And this tool is going to select relevant features for training the machine learning algorithm on data that is test set data. And nobody's going to know. And you're going to get bad results in science. So you could see the same kind of thing happening potentially in your careers, right? You're data scientists. You make a tool. You ship that tool to somebody else who's going to use it. Somebody in the sales department is going to use this tool, and they don't know squat. So if you allow them to make bad procedural errors with your tool, they're going to make them. If you make a mistake and encode a procedural error into this tool, there's no way this salesperson's going to know. All right. So let's finish off by talking about errors of human cognition. Oh, whoops, actually we're not quite finished yet. So we're going to talk about errors of human cognition. There are many, many different kinds of biases that we humans have. So I'm not just talking about racial bias here. I'm talking about various kinds of ways that your mind works that bias you to see the world in a certain light. And this can include racial bias. I mean, racial bias is, fundamentally like me is good, not like me is bad. Okay? That's how racial bias can be seen, at least partially, as that kind of preference for just like me. So there's a number of these things. And most relevant to data science, maybe, is, let's see, where is it here? These ones are written here. Confirmation bias. Okay? So we're going to talk about confirmation bias, but just in general, before we do, let's just kind of get a sense of the different kinds of things that psychologists and so forth have figured out about how we work. Okay? We suffer from problems of too much information. As we're assaulted by information, we just have to cut it down and look at things in ways which help us make decisions, right? So we don't actually see everything about a situation. We're going to see small chunks of the situation. Our minds are biased to picking up particular things, right? We're going to enjoy weird humor more than we're going to enjoy boring lectures. We're going to enjoy, being drawn potentially to details that confirm our own existing beliefs, like confirmation bias. And we may be blind to our own problems. We may notice flaws in others that we cannot find in ourselves, right? We notice things are more often when they're already primed in our memory or repeated very often. So we're more likely to know repeated elements than things that are rare. Okay? So confirmation bias you may have heard of. And if you haven't heard of it, you've probably done it. Okay? So people tend to allocate a lot of confidence in their beliefs. And if they're presented with evidence which may contradict it, you're not necessarily going to pick up on that. Okay? Somebody who's doing confirmation bias only appreciates the facts that support their hypothesis. They ignore or misinterpret or just forget about things that might challenge their worldview. So how can you avoid this? How can you avoid being this person? Clearly, you've got to work at it because your mind is predisposed to just, assume that everything that your preferred political candidate does that is bad, everything your political party does that's bad, it's not intentional. It's just, stuff happens, right? And it's not important. But if the same thing happened to the political party you don't support, you would take this as strong evidence of how corrupt and nasty they are, and we've always known that they're terrible people, right? So if you want to avoid this kind of thinking, you've got to work hard at it. You've got to question yourself more harshly than you question others. You've got to ask questions that test your beliefs rather than asking questions that confirm your beliefs. So let me show you an example. Let's do a little class participation. So here is an example of a number sequence, 2, 4, 8. I'm going to ask you, the audience, to shout out with number sequences that you think are congruent with the rule I'm espousing here. Whatever rule is generating this sequence, can you tell me another set of numbers which is going to fit that rule set when I'm going to say, yes, it's the same kind of sequence. No, it's not the same kind of sequence. All right, ready? Go. Yes, 4, 6, 8 is in the same sequence. Yes, you up there. 4, 8, 16, 32, Same sequence. Yep. 32, 64, 128. Yep, in the sequence. You've got it. Anybody else? Yes. 12, 14, 16 is in the sequence. But can anybody tell me what the rule is? Can you articulate to me what the rule is? What's causing this? No, it's not. That's not it. I'm sorry. It's not even numbers. What is it? Have you figured it out yet? Somebody else want to guess? How can you find out whether your assumptions are the right assumptions? That's right. You should construct an example that tries to break your assumptions. Rather than just going with things that if you think, oh, it's even numbers, let me just throw out even numbers. Or I think it's multiply by 2, so I'm going to just keep multiplying by 2. That doesn't tell you anything, right? If you want to understand whether your assumptions are right, you've got to try to break them. So if you think that it's even numbers, then you're going to have to throw out 3, 5, 9, right? And see if that breaks it. Nobody did that. The person that asked even numbers, they threw out an example right beforehand that was just even numbers. And this is just the way our minds work. We don't try to break our own assumptions so easily, not without training. So can anybody tell me what the example is that's going to break this? What is absolutely not going to be in the sequence? Yes, Marilyn Monroe. You're right. There we go. 842 is not in the sequence. And you're right. You've guessed it. So the rule is ascending, monotonically ascending numbers. So it was hard to see because nobody is inherently going to go ahead and challenge their own beliefs so harshly, not without training. So confirmation bias like this can also play a role in making it hard for you to fix software problems. So when you are dealing with some program of yours failing, what do you have to do? You have to stop and ask yourself, what are my assumptions? What do I think is going on here? Okay, once I have an idea, how can I prove to myself that other things are not happening? Well, I'm going to try to break my assumptions. Okay, if I think that my test goes through like this, and I assume that test is good because, I don't have any problems at that stage, well, maybe I should try to break my assumptions. Maybe I should try to purposefully manipulate bad data in that test and see if it replicates my problems. So the same kind of thinking that is important for analysis is also important for debugging. Okay, so more cognitive biases. Our memories are really whack, right? So they don't work the way you think they do. Memories in your mind don't function like, information written in a file and stored in a file drawer. They don't function the way computer memory does, which it stores it, right? And it comes back exactly that way. No, if you want to understand memory, two things that can be useful for a data scientist is to understand that your working memory, your ability to hold something in your head for a few seconds or minutes, it has a limited capacity. You can't keep more than a few pieces of information in your head. Somewhere between, say, 3 and 7 is the classic thing. Or maybe it's actually just 4 and 2 in each side of your mind, isn't it? But whatever, that's biological research. Okay, So there's a few items you can keep in your head. So only those items can be stored at any one time, and if you bring something new in, then you're going to lose track of something old. But what you can do is you can chunk up your memory. You can hold one unit, right? One chunk in your memory. So you can hold maybe 4 chunks, but what those chunks are can be done differently. So you can memorize individual letters, A, B, C, D, right? Sorry, I shouldn't do that right. You say remember E, X, Z, N, right? You can measure those 4 chunks. Or we could measure 4 words: Abe, Baker, Delta, Niner, right? And you can remember 4 words. So if you want to remember more stuff, you have to form chunks at higher levels. Okay, and understanding how memory works that way can be helpful not just for your own performance, but it can be helpful for understanding how to communicate with other people. Never throw information at somebody like a fire hose, right? You want to give them information from an analysis. You need to give them time to absorb something. And if you want them to think with it, you need to only give them a couple of items and let them manipulate a couple of items. Another good thing to realize is that the way your autobiographical memory works, the way your memory of being here in this lecture works, is that it puts together a lot of different things at once that happen over time. Okay? That kind of temporal element of putting things through a sequence of your experience, you're going to remember sitting down, going through all this lecture, you're going to remember falling asleep right about this point, right? You're going to remember how cold the room was while you were falling asleep, right? And you're going to remember the feeling of the fact that you're struggling to stay awake, of how hard the chair was on your bottom, okay? This is the way autobiographical memory works. It puts together lots of different senses over a sequence of time, and it has a very strong component of emotion. So if I said something terribly upsetting to you right now, you're dang sure going to remember that I said something so horrific. Okay? So if you want people to remember information that you're giving them, you should do something to hijack their biases. All right. So I'm going to skip a few things just because we are running ridiculously long on time. But you can look at the framing effect on your own. And the framing effect is a cognitive bias that shows you that if you tell somebody something positively, then they're going to have a very different reaction to it than if you tell them the exact same fact in a negative cast. Okay? So, yeah, we definitely want to take advantage of these things, right? We want to use our cognitive biases for good communication. So don't do things that are just anecdotes, or as we call them, anecdata, when you have 2 data points, right? You want to do a rigorous analysis and then communicate it via an anecdote, which is much more relatable to somebody's cognition than just throwing an Excel table at them, right? So do the rigorous analysis and then go ahead and use the anecdote to communicate with, but back it up with the real deal. Okay. I want to close finally here, now that we are going to be way past time, with talking about errors of communication. So the Space Shuttle program suffered 2 losses. The Challenger in the 80s exploded because of a problem with the solid rocket boosters. There was a joint between 2 sections of the rocket that failed because the temperatures were too low. And the Columbia was lost in 2003, I think, because a piece of foam broke off during launch off of the fuel tank, and it whacked the leading edge of the orbiter's wing, and it put a hole in the wing. Okay, and when the orbiter tried to re-enter to come back to Earth, hot air moving at 14,000 miles an hour got inside the wing and blew up the craft. So why? Why did these disasters happen? Well, it turns out that both of them have been traced to problems of communication of technical data. So if the technical data had been better communicated through the chain of command, then these disasters might have both been averted. So this is the conclusion from Edward Tufte. He is an expert in data visualization. I've mentioned him in the past. This book right here is one of his, and it is a classic in understanding how to communicate visually. So he led the investigation into these issues and how the communication broke down. So this is the way that the engineers were communicating to their bosses about the Challenger's cold weather launch, right? So what they were using were these cutesy graphs that have pictures of the boosters on them, right? And they were marking where on these graphs where the damage was occurring and how severe that damage was with these obscure little tick marks. So more tick marks, I think, means more damage, but I'm actually not sure after even studying this diagram for a fairly long time. And you'll see on each booster a notation about the temperature, about where, what temperature it was when this booster had this damage. Okay? So this is a lot of visual information, and almost none of it is relevant to the problem of understanding, hey, is it too cold to launch the damn space shuttle? So if instead of presenting in this kind of method, if they had done something much more direct, where they graphed, so along this axis, the temperature at the time of launch, and on this axis, how much, some sort of damage indicator, right? How much damage there had been, they would have been able to see from all the dots of all the missions that maybe there was something like potentially even an exponential in here, where going much lower was going to result in extreme damage to the booster. Okay? And this is where shuttle launch took place on the fateful day of the Challenger, down below freezing. So totally a new regime where nobody had ever visited before. But this kind of communication of that is crap for showing you the important aspect here. So presenting data this way enabled managers who were probably half asleep during the presentation anyway and bored with the technical detail. They just took these slides and they went to their bosses, and they maybe didn't communicate very well with their bosses. And in a game of telephone, more and more information was lost as these slides kicked up the chain of command. And by the time it got to the top where people said go or no go, they were not getting the right information at all. They were only looking at these slides that had been passed up from the deck and not hearing the right negative words that the engineers were saying. So the Columbia is the same kind of deal. The Columbia, they knew when the shuttle was launched, they knew that the wing had been possibly hit by foam. They had seen it on cameras on the way up. Well, they had to figure out, was there any hazard to the orbiter? So engineers on the ground did the analysis, and they said, okay, here's our two models, and our models are saying all this stuff, and we're communicating this stuff to our managers. What is being said here, right? I mean, this slide is so dense, so incredibly dense with words, and most of it's jargon, and it's repetitive, and it's laid out in a poor way where you can't really quite figure out what it's saying, okay, but what is it saying? Well, if you look at the title, Review of Test Data Indicates Conservatism, you might think that the tests they did, the simulations they ran, show that it's conservative, that, it's everything's safe. That's not what it's saying at all, right? This is where the real information is at. The flight condition is significantly outside of the test database. So what they're saying here is that this number here, 1920 cubic inches of foam, is 640 times the size of the test element that they used to try to figure out if this could be a bad problem. It's unlikely that something that's 640 times larger than the thing you used to build your model means that your model is any good, right? So again, the same thing happened. This was a negative result that was couched in techno jargon that was impenetrable, and it wasn't communicated with enough oomph at the moment, either in the slide or by the engineers themselves. So in those cases, we're going to see that it kicks up the chain of command. There's pressure to perform and to send the shuttle home, right? And nobody understands what's going on here. So if they had said a slide that looked a little bit more like this, our models are irrelevant. Debris hitting the wing is 640 times larger than the experimental data we used to build our model, so we have no clue what will happen on reentry. If you had a slide like this, then very likely they would not have made the decision to go ahead and try to bring the orbiter home. They would have sent out a rescue mission maybe. Okay, so communication is key. In the end, if you don't communicate with not just your teammates, but the decision makers who are using your analyses, you're not going to get good results, okay? And all of this good communication starts with a relationship. So you need to have friendly, cordial relationships with everybody that you work with and with your clients. You need to be able to talk to subject matter experts and have them trust you. You need to have people believe the analyses that you're doing. And they're not going to believe them unless they think you're an okay person, right? They're not going to believe them necessarily or listen. Maybe they do believe them, but they don't care and they won't remember, right? Unless they think you're pretty on the ball and that they like who you are, right? So developing a relationship is key to getting things done. Also important, listening. You are hired by a client, or you are, asked by your boss to do something. Listen to them. Don't jump off the handle and assume you know what they're talking about. Ask them questions. Try to develop, am I really understanding this, right? Remember to check your confirmation bias. Try to break the system, right? Ask questions that test your understanding. So if I'm right and I ask this question and I get a no answer, that doesn't work. If I get a no answer to this question, what I think cannot be true, okay? So ask testing questions of yourself and of the situation. When you do find some problems, you should definitely, because you have those relationships where you're with people, once your analysis uncovers that it's, oh my God, too cold to launch this space shuttle, then you should be able to use those relationships and the goodwill you've built up by listening and asking. You should be able to use those relationships and lever them to get people to pay attention to your alarms. Okay? So at that point, you have a really good system whereby you can communicate with everybody, but you also need to use tools the right way, right? We've talked about Excel's failures and things like that, But there's also tools for communication that need to be used properly. You need to be able to broadcast your results out to the people that matter, right? It's no good if you can't communicate. You can communicate with your team, but you can't get your boss's boss to listen, right? So you need to use tools to get stuff to their attention. Okay. And I think that's about as much as I can communicate tonight. I appreciate your patience and slogging through this extra 15-ish minutes that we threw at you. I hope you have a very nice evening, and I look forward to delivering one final lecture. Before we go, please do remember to fill out CAPES. Okay? Probably should have put that at the beginning. You're not going to be listening right at this point. So please fill out your CAPES, and I will see you next time. Bye.